A study of the hardening of steel shows that steel can be hardened by heating and quenching. Hardness, however, is only one of the useful properties of steel. Toughness, for example, is frequently essential. But fully hardened steel is not tough. On the contrary, it is usually brittle. Some steel parts, like this ball bearing, call for high hardness to resist abrasion, while only a moderate degree of toughness is needed. Other steel parts, like this automobile spring, require toughness to resist impact or shock, but also must be hard for resiliency. These gun parts, called front guides, have been fully quench hardened. The steel is quite brittle. It lacks toughness. To make this type of steel tough enough for service conditions, it is tempered. Tempering, or drawing as the process is also called, is a method of toughening steel after it has been hardened. In the toughening process, the hardness is reduced. When we speak of toughness, we need a quantitative guide, an accurate means of measuring it. The Charpy Impact Toughness Testing Machine answers that need. It determines the resistance to impact offered this pendulum by a specially prepared specimen bar of the steel under test. The specimen is placed across the pendulum's line of travel. The pendulum is drawn back to a fixed angle. When the pendulum is released, the energy required to break the specimen reduces the swing of the pendulum. This dial registers the pendulum's travel. It measures in foot-pounds the energy required to break the test piece. This is a measurement of the steel's toughness. When previously hardened steel parts are to be toughened by tempering, they are first reheated. Tempering temperatures are below the steel's lower critical temperature, the temperature at which the steel first began to harden. The parts are kept in the furnace until they are uniformly heated. Thus, tempering time depends on the thickness of the pieces and the temperature to which they must be brought. After heating, the parts are removed from the furnace and allowed to cool in air. What has happened in this process to change the properties of the steel? Here are 5 micrographs of an SAE 1043 steel, which show its structure after tempering at progressively higher temperatures. In each stage pictured here, the steel is tougher than in the previous one. The first micrograph is of the fully hardened steel. It shows the typical martensitic structure of plain carbon steel at maximum hardness. The steel's Rockwell C reading, the measurement of its hardness, is very high, 60. On the other hand, its Charpy reading, the measurement of its toughness, is very low, 3. After tempering at 400 degrees Fahrenheit, only a very slight change in structure has taken place. It is still essentially martensitic. Point 2, and by its Rockwell C reading, which is down 4 points to 56. When the steel has been tempered at a higher temperature, 650 degrees, a recognizable change can be seen in the structure. The carbide has started to precipitate from the martensite. The carbide appears black in the micrograph. The toughness, however, has barely changed. It is now at 6.3, even though the hardness has decreased to 49. It is necessary to go to higher temperatures to obtain marked toughening. Tempering at 900 degrees produces a further precipitation of carbide from the martensite. These carbide particles, diffused in the martensitic structure, are beginning to coalesce. Now the steel's toughness has jumped to 22. Its hardness is down to 39. This micrograph shows the steel after tempering at 1275 degrees, a heat closely approaching its lower critical temperature. A definite coalescence of the carbide particles has taken place. This is discernible where the black lines have broken up into dots. The steel is now very tough. Its Charpy reading is 65, but it is quite soft. Its Rockwell C is 20. From these and additional test data, a graph can be made to illustrate the relation between the toughening of the steel and the accompanying change in its hardness. As abscissa, we have the tempering temperatures in degrees Fahrenheit. As ordinates, we have the Charpy impact toughness in foot-pounds. We plot the values obtained by testing our steel after tempering at progressively higher temperatures. These points give us this curve. Now we also plot as ordinates the hardness readings of the steel at the same tempering stages and obtain this curve. We can see that there is a generally consistent relationship whereby hardness decreases as toughness increases. But there is an exception to this rule. Between 450 and 650 degrees, toughness actually decreases a little. However, there is no corresponding deflection in the hardness curve. This is called the brittle tempering range. But at temperatures above this range, and particularly beyond 800 degrees, the toughness increases very markedly. The same graph, drawn for any other plain carbon steel, would show a similar relationship between toughness and hardness. Normalizing is a heat treatment employed on steel forgings or castings, for example. These forged pieces are being placed in the furnace to be normalized before they are machined. Normalizing removes undesirable coarse grain structures that may have occurred during hot mechanical working in the forging process. Similar coarse grain structures occur in castings while solidifying. Normalizing produces a more uniform grain structure, better adapted to subsequent heat treatment. Sometimes normalizing alone is a sufficient treatment for obtaining the mechanical properties desired in the final steel. In normalizing, the steel is heated to a temperature from 100 to 200 degrees Fahrenheit above its upper critical temperature. In this case, 1600 degrees. Here again, the parts are held at sustained temperature until they are uniformly heated. After heating, they are removed from the furnace and cooled in still air. Slow cooling in air is essential to complete the normalizing process started under the influence of high temperature. Here is what happens during the normalizing process. Before normalizing, the crystal structure at these 2 points looks something like this, coarse and non-uniform. Notice the considerable difference in the size of the individual crystals. Furthermore, the crystals in the wide section are relatively larger than those in the narrow section. As the part is heated to high temperature in the furnace, its varied crystal structure changes to one which is uniform throughout. Normalizing reduces the size of all the crystals. The result, a uniform, fine-grained structure. Another process which, like normalizing, prepares steel for subsequent operations is annealing. Annealing is a stress-relieving process. This process also requires heating the parts in a furnace. Annealing has two principal functions. It relieves stresses occurring in the steel as a result of such operations as cold rolling, extruding, spinning, or punching. And secondly, since it induces softness and ductility, it is frequently employed to facilitate mechanical working like bending, shaping, or machining. In full annealing, parts such as these, made of plain carbon steel, are heated slowly to about 75 degrees Fahrenheit above their upper critical temperatures. In this case, 1,525 degrees. To assure an even temperature throughout the piece, it must be held at the proper annealing temperature for about 1 hour per inch of thickness. Then the heat is shut off, and the material is allowed to cool slowly in the closed furnace. This shows schematically the stresses induced in this part by previous operations. Under the influence of the high annealing heat, the stresses disappear. The slow cooling in the furnace prevents their return. Thus, when finally removed, the parts have been relieved of all stresses. In addition, they have attained a maximum softness and ductility, which makes it possible to machine them more easily. To sum up, tempering, normalizing, and annealing are basic processes in the heat treatment of steel. In tempering, employed to toughen a previously hardened steel, heat uniformly below its lower critical temperature and cool in air. In normalizing, employed to remove coarse grain structures in forgings or castings, heat uniformly to from 100 to 200 degrees Fahrenheit above the steel's upper critical temperature and cool in air. In annealing, employed to relieve stresses and to increase ductility, heat uniformly, in case of full annealing, to about 75 degrees Fahrenheit above the steel's upper critical temperature and cool in the furnace. Thus, through controlled heating and cooling, specific changes in the properties of steel are achieved.